So I have to illustrate what I'm
Sure.
saying here in a couple of important examples. Okay, so let's have a look at this elementary problem, which every primary school student who has done some fractions will know. So if 1/2 plus 1/3 plus 1/5, if I evaluate that, I get 31/30. And we can accept that, a primary school student who's learning fractions ought to be able to make this calculation. Now, suppose that I want to demonstrate, real number arithmetic, which involves things like x plus 7 or cosine of 5 or the square root of 11 or something like that. If I try to, well, my favorite example, which I'm always telling people is this one here. So I should, for consistency, write it down. What is pi plus e plus square root of 2? Okay, so my computer is pretty smart. And if I ask it to calculate this, just to evaluate it, you see what it gives me? It gives me the same thing back again. And this is not just because of this program. If you ask Mathematica or pretty well any other program, to calculate, to do this arithmetic, you're going to get something similar. But it's not just this. I can do this in a myriad of different ways. I could take log 4 plus tan of 7, and I ask my computer, what is that? That's another example of a calculation. Or I could ask, what is cosine of 3 times sine of 7? Oh, it doesn't. Maybe it doesn't.
You have a problem with this because I'm sure there's a way that you can get it to do a decimal expansion.
Oh yes, I can do that. Yes, absolutely. So I can evaluate these things numerically very easily. So I can evaluate this numerically. I can evaluate all of these numerically, and it's the numerical evaluation that an applied mathematician is going to use. So the applied mathematician only needs to work to 4 or 5 decimal places. Maybe if you're a theoretical physics student, maybe to 10 decimal places in some strange situations, but typically to just a few decimal places. So that's not a problem. But from a pure mathematics point of view, this idea that we have a valid arithmetic of real numbers is, it would seem, contradicted here, right? Here I'm taking very simple real numbers and I'm performing very simple arithmetical operations on them, and I'm not getting any kind of calculations. The reality is my computer and almost all computer programs that I know of are incapable of doing real number arithmetic. And you can frame that, we have various framings of real number arithmetic in pure mathematics. We talk about Dedekind cuts, and we talk about equivalence classes of Cauchy sequences. There's continued fractions. There's other ways. It doesn't matter how you frame it. The computational reality is always the same, that you can't actually compute exactly these operations on relatively simple real numbers.
What do people who are analysts say to you in their response or their objections?
So an analyst is going to be very uncomfortable with this conversation. You see, before Dedekind came along with his theory of Dedekind cuts, people knew about these problems a lot, because for centuries earlier, people had been making computations.
What is it exactly that the analyst may put to you as a rebuttal?
Yeah, so most analysts are going to be uncomfortable with this train of thought, because historically, long before Dedekind cut theory came about in about the 1870s, the working prototype of a real number was an infinitesimal, a so-called infinitesimal. And it's not too hard to see that if you want to have a theory of arithmetic with infinite decimals, that's going to be problematic, because the infinite nature of the decimals means that it's going to be difficult, or actually impossible, to prescribe what the operations are. So to be specific, suppose that you're given 2 computer programs that will output the nth digit of 2 decimals, and you're asked to write another computer program that will output the nth digit of the sum of those 2 real numbers.
You just said the
Okay?
nth digit of 2 decimals. You mean the nth digit of the sum of two numbers, or?
Yeah, so let's say you want to sort of incorporate real number addition on a computer in a computational fashion. The inputs are two infinite decimals given as programs that will calculate the nth digit,
Infinitesimal. I see.
and your
Okay.
output is supposed to be another program of the same kind, which represents the sum of those two things.
Mm-hmm.
So if you think about this for a little while, so the way kids are taught decimal number arithmetic in school is you have two decimals. To add them, you start on the right-hand side. And you start on the right-hand side, and then the carries go to the left. And so then you pick up the carries as you proceed from right to left. The problem is if you have two infinite decimals, if you have in some sense, there's no right point to start with, right? So what you have to do is you have to typically sort of truncate and do some partial calculation, then go further, truncate again, do the calculation again, and modify what you've got every time you go. But the problem with that is there's the problem of carry of nines. So at some point you have the potential of getting a lot of nines, so that you're never in possession of a program that will guarantee that you've got the nth decimal place, because that nth decimal place could conceivably depend on stuff that's happening very, very far down the track, and you don't know how far. That's the critical thing. Okay, so at some level, analysts would have been aware that in terms of a theoretical number system, infinite decimals don't really work. This is why the 17th century people, 18th century people didn't create such a theory. They would work with decimals all the time, but they didn't have a theoretical understanding of those, and then they kind of avoided it because they knew of these difficulties. So the Dedekind cut story, the Cauchy sequence equivalence class story, these are attempts by pure mathematicians to kind of circumvent these difficulties, would not face them squarely on and surmount them, but to actually sort of circumvent them and make it look like we have an arithmetic of real numbers when we don't. We don't have a valid arithmetic of real numbers. That's just the way the world is. And it's not because we're not smart enough. It's because we're attempting something that's intrinsically impossible. What we end up having to do is we have to then separate our mathematics from computational reality. We have to kind of go up, and go up on stilts so that we never touch the floor. We're walking around on these stilts and not looking down, just always looking up. So this means a lack of contact with mathematical reality ultimately. And that manifests itself across, I could talk for hours about these manifolds, varieties, topological vector spaces, Lie groups, there's so many areas of mathematics that get disrupted by the weakness of our underlying numerical system, the so-called real numbers, or the associated complex numbers.
I think it'd be a great time to give an example of a problem that arises when one doesn't take this computational view. For example, in physics, we use E all the time. It's rare to find a formula without E. So what is the solution? We just replace this with something else? Is physics breaking down in some way? Now, I know with Feynman path integrals, you can solve it by saying it's finite.
No. I think I think you physicists are fine, because you're not thinking of this E as an infinite decimal. You're thinking of E as a finite decimal of some variable number of decimals, which you can kind of choose. You can choose the amount of a resolution depending on the problem that you have in mind. So you're playing along with the pure mathematician's notation because you've gone to math class, you've learned about E and so on. But effectively, you're adopting an applied mathematical point of view, which doesn't require the infinite decimals. And you're actually working in a numerical system, which is an approximate decimal system, which is not the real number system. It's what the computers actually do. You have some finite number of decimals, and you have to work with that, and you have to deal with truncations and round off and so on and so forth.
Right. Now, there's this physicist, I'm unsure if you've heard of him. His name is Nicholas Gisin.
Mm-hmm.
Have you heard of Nicholas Gisin?
Yeah, I have.
His argument against the reality of the real numbers goes as follows. I think it's an argument more about discrete space-time, though I don't know if that's exactly the case. If an electron carries with it its space-time point, it would have to carry an infinite amount of data to specify a certain real number, and thus it would create a black hole. Now, I don't know if I buy that argument per se, because it means that the electron carries with it its space-time point. I'm unsure what that means. But for people who feel like what you're saying is radical, in many ways, some physicists already are in line with this thinking.
I think you're absolutely right. And in but 20th century physics has squarely acknowledged the fact that our underlying space-time is not infinitely divisible. See, the model of the continuum as the real number line, it really assumes an essential infinite divisibility of the line, right? That's the point. And you've got as many decimals as you want. So every time you add a decimal, you're dividing by 10. Okay, but physicists know that that's not the way the world is. You get down to 10 to the minus 30 or whatever, and you add a Planck scale, and then that divisibility just erodes.
I have a physics question for you. So in quantum mechanics, if you have let's take the most basic wave function, and let's say that the wave function is real. Some people say the wave function is real, whatever that means. Well, people who believe in the multiverse say it's the most real. There's only the wave function. Okay, now let's say we have a simple system where it's half-half, so half up, half down. Okay, then the wave function itself has 1 over square root of 2 because you have to square the wave function to get half. Are you saying that 1 over the square root of 2 is not, the wave function cannot be that because the square root of 2 does not exist?
No, that's just to obtain a kind of a uniticity, a unitarity. How should I say? You can easily have equal extent in this direction, equal extent in this direction. Like you can have the point 1, 1. Okay, so the point 1, 1 in the plane. Okay, its distance from the origin is square root of 2. But in rational trigonometry, which is my preferred way of thinking about metrical geometry, it's not the distance that matters. It's the quadrants. It's the square of the distance. It's the sum of the squares.
Okay.
So if you adopt a rational trigonometry point of view, those kind of objections having to do with distance more or less disappear. So this is like preferring Einstein's interval to the square root of the interval, to not insisting that we take square roots of our metrical quantities, just to stick with the metrical quantities themselves, the natural quadratic ones.
Let's say you're speaking to a quantum physicist who constantly has to take the square root in a sense because the square is what the wave function's probability is, the probability distribution is the square. So you're saying that is the fundamental quantity, not the wave function itself? Sorry, that is the real quantity. The probability distribution is the real quantity. Forget it.
No, I wouldn't say that. I would have to be better versed in physics and have an opinion on the nature of quantum mechanics to be able to say that. I think it's very interesting, but I don't have a strong opinion as to the true role of the wave function and how it should be interpreted.